Welcome to this coding problem walkthrough. Today, we'll be diving into problem number 1980, find unique binary string. In this problem, we'll explore how to identify a binary string that is not present in a given list of binary strings. Stay tuned as we examine approaches to solve this intriguing challenge. In this problem, we are given an array of binary strings called nums. Each string in the array is composed entirely of the characters 0 and 1, and all the strings are of the same length. Our goal is to find and return a binary string that does not exist in the input array nums. If there are multiple valid answers, we can return any one of them. However, the binary string we return must have the same length as the strings in nums. For example, if all strings in nums are 2 characters long, the output string must also be 2 characters long. This ensures consistency between the input and the result. Let's look at the first example to better understand the problem. Here, the input array nums contains the strings 1 foot and 10. Since we need to find a binary string that is not in this array, we can see that 2000 foot is a valid choice because it is not listed in nums. Another valid option would be 11, as it is also absent from the input array. Both are acceptable answers because they satisfy the conditions of the problem. They are binary strings of the same length as the strings in nums and they do not appear in the input. In the second example, the input array nums contains 2000 foot and 01. A valid output is 10, as it does not appear in the input array. Additionally, 11 would also work as an answer because it is not part of nums. This highlights an important point: there can be multiple correct answers to this problem, and we are free to return any one of them as long as the conditions are met. The key is identifying any string of the appropriate length that is missing from the input. Finally, in the third example, the input array nums is 111, 011, 001. From this input, a valid output is 101, as it does not exist in the input array. Again, other options like 000 or 110 could also work, as they are absent from nums. The problem also provides some constraints and edge cases to consider. For instance, the length of nums can range from 1 to 16, and each string in the array can be up to 16 characters long. Additionally, all strings in the input are guaranteed to have the same length. Edge cases might involve very small or very large input sizes, or situations where nums already contains all possible binary strings of a given length. These considerations will help guide us toward an efficient solution. To solve the problem of finding a unique binary string not present in the input array nums, one approach we can consider is brute force. The intuition here is straightforward: if we generate all possible binary strings of the same length as those in nums, we can simply check which one is missing. Since there are 2 n possible strings for a length n, we would generate each string and compare it against the input. To make this efficient, we can convert nums into a set, allowing for constant time lookups when checking if a string exists in the input. The steps involve generating these binary strings using techniques like recursion or bit manipulation, and returning the first string that is not found in the set. However, this method has significant trade-offs. While it guarantees a correct result, it's computationally expensive due to the exponential time complexity. Generating and checking 2 n strings quickly becomes infeasible as n grows. Additionally, it requires substantial space for storing the generated strings. This makes it an impractical solution for larger input sizes. An optimized approach leverages a more elegant mathematical insight. By applying a variation of the Cantor diagonalization argument, we can directly construct a binary string that's guaranteed to be unique without needing to generate all possible strings. The idea is to create a new string by flipping specific bits. Specifically, for each ith string in nums, we flip the ith bit and append the result to our new string. This ensures that the newly constructed string differs from every string in the input at least at one position, specifically the ith bit for the ith string. This guarantees uniqueness without requiring further checks. The steps are simple: initialize an empty string, iterate over the input, flipping the bits as described, and return the result. Key observations here include the fact that this construction inherently ensures the new string is unique, eliminating the need for set lookups or additional verification. In terms of complexity, this approach is highly efficient, with time complexity of O(n) for a single pass through nums and space complexity of O(n) to store the resulting string. Although the optimized approach may seem less intuitive initially, it offers significant advantages over brute force. It avoids generating all possible binary strings, making it far more efficient and scalable. The assumption that all strings in nums are of equal length simplifies the problem and aligns with the constraints provided. Ultimately, this diagonal argument is the chosen strategy due to its elegance, correctness, and linear time complexity, which makes it practical for larger inputs. While brute force is conceptually simple, its exponential time complexity renders it impractical for real-world usage. The optimized method avoids unnecessary computation, directly constructs the solution, and ensures scalability, making it the ideal choice. By balancing efficiency and correctness, this approach demonstrates how mathematical reasoning can simplify complex problems and yield powerful solutions. The problem we're tackling involves finding a binary string of length n that is not present in a given array nums. Binary strings are sequences made up of only the characters 0 and 1. The key observation here is that the array nums may not contain all possible binary strings of length n. For instance, if n equals 3, there are exactly 8 possible binary strings, ranging from 000 to 111. If nums contains fewer than 8 strings, at least one of those binary strings must be missing. The brute force approach to solve this problem is straightforward: generate all possible binary strings of length n and compare each one against the strings in nums. This guarantees that we will find a missing string, though the method may not be the most efficient for large values of n due to the exponential growth in the number of binary strings. To implement the brute force approach, the algorithm follows a series of steps. First, we validate the input by checking that the array nums contains binary strings of uniform length n. Next, we generate all possible binary strings of length n. For example, if n equals 3, the strings range from 000 to 111. These strings can be generated through iteration or recursion, and we store them in a set called all_binary_strings for efficient lookup. We then convert nums into a set, nums_set, to enable O1 lookups. With these two sets in place, the algorithm searches for the missing binary string by iterating over all_binary_strings and checking whether each string exists in nums_set. The first string that is absent from nums_set is the one we return as the solution. Once a missing binary string is identified, we immediately return it and terminate the process. This ensures that the algorithm minimizes unnecessary computation. Using sets for both nums and the generated binary strings is important because it allows for fast lookups, which significantly improves the efficiency of the algorithm. However, the brute force approach still has a worst-case time complexity of O2 to the power of n. This is because generating all binary strings requires O2 to the power of n time, and checking each string against the set also takes O2 to the power of n in total. Although this approach guarantees correctness, its exponential complexity makes it impractical for large values of n. Despite this limitation, the simplicity and clarity of the method make it a good starting point for understanding the problem. Additionally, the use of sets ensures that the implementation is both intuitive and efficient for small input sizes. Let's illustrate the brute force algorithm with an example. Suppose nums is 000, 001, 010, 011, and n equals 3. First, we generate all possible binary strings of length 3, which are 000, 001, 010, 011, 100, 101, 110, 111. Next, we convert the input array nums into a set, resulting in nums_set equals 000, 001, 010, 011. Now, we iterate through all_binary_strings. The first string that is not found in nums_set is 100, so we return 100 as the missing binary string. We also need to handle edge cases. If the input array is empty, the first binary string, 0*n, is returned. If nums contains all 2*n binary strings, we could return an appropriate message, though this scenario is outside the problem's constraints. Finally, if nums contains invalid strings, such as those with non-binary characters or inconsistent lengths, the algorithm should raise an error. The brute force approach comes with clear time and space complexities. The time complexity is O2 to the power of n, as we generate all possible binary strings and check each one against the input set. Similarly, the space complexity is O2 to the power of n, because we store all the binary strings in memory. While this approach is computationally expensive, especially for large n, it guarantees correctness and is simple to implement. To optimize for larger values of n, we could explore alternative methods that avoid generating all binary strings explicitly. For example, bitwise manipulation or a greedy approach might allow us to construct a missing binary string directly, bypassing the need to store or iterate through the full set of possibilities. These advanced techniques can help reduce both time and space requirements, making the algorithm more scalable. The problem find unique binary string requires finding a binary string of length n that is not present in the given list of binary strings, nums. This implementation uses the diagonal flipping technique to construct such a unique string efficiently. Explanation. 1. Initialization. We determine the length n of the input list nums. Since all strings in nums are of length n, this also represents the number of rows, or strings. 2. Diagonal traversal. For each index I from 0 to n1, we build a new binary string by traversing diagonally through the matrix formed by the binary strings. Specifically, we examine the ith bit of the ith string. 3. Flipping bits. To ensure uniqueness, we flip the ith bit of the ith string. If the bit is 1, we append 0 to our result. Conversely, if the bit is 0, we append 1. This guarantees that the resultant binary string differs from every string in nums at least at one position, the diagonal position. For result construction, the flipped bits are collected into a list, which is then joined to form the final binary string. 5. Return value. The constructed binary string is returned as the result. Since the diagonal flipping ensures uniqueness, this solution is both correct and efficient. Complexity. Time complexity, O(n), as we iterate through the diagonal once. Space complexity, O(n), for storing the result string. This solution leverages properties of binary strings and diagonal traversal, avoiding exhaustive search and ensuring uniqueness deterministically. This is the Java implementation of LeetCode problem number 1980, find unique binary string. The logic mirrors the Python solution by leveraging diagonal traversal to construct a binary string that differs from all given strings in the input array. Key differences include Java's use of the string builder class for efficient string manipulation and explicit type declarations. The charat method is used to access individual characters, and the result is built by flipping the diagonal bits. This ensures the generated string is unique. To start, we're given the input nums equals 0, 1, 10. This means we have two binary strings, each of length 2. Our goal is to find a binary string of length 2 that does not already exist in this array. First, we initialize two variables, n, which is the length of the binary strings in nums, and it equals 2 in this case, and result, which is an empty list where we'll build our unique binary string step by step. Now, we perform a diagonal traversal through the binary strings in nums. This means we loop through the indices of the binary strings, from 0 to n1. In the first iteration, where I equals 0, we check the first character of the first string, nums, 0, 0, which is 0. To ensure our result is unique, we flip this bit from 0 to 1 and append 1 to the result list. At this point, result equals 1. In the second iteration, where I equals 1, we examine the second character of the second string, nums, 1, 1, which is again 0. Flipping this bit gives 1, and we append it to result. Now, result equals 1, 1. After finishing the traversal, we join the elements of result into a single binary string, which gives 11. This string is not present in nums, so it is our unique binary string output. For the next example, the input is nums equals 111, 011, 001. Here, we have three binary strings, each of length 3. As before, we initialize n equals 3 and start with an empty result list. We then begin the diagonal traversal. In the first iteration, where I equals 0, we check the first character of the first string, nums, 0, 0, which is 1. Flipping this bit gives 0, so we append 0 to result. At this point, result equals 0. Next, for I equals 1, we examine the second character of the second string, nums, 1, 1, which is also 1. Flipping it results in 0, and we append 0 to result, making result equals 0, 0. In the third iteration, or I equals 2, we check the third character of the third string, nums, 2, which is 1. Flipping this bit gives 0, and we append it to result. Now, result equals 0, 0, 0. After completing the traversal, we join the elements of result into a single binary string, resulting in 0, 0, 0. This binary string is not found in the input array nums, so it is the unique binary string we were tasked to find. In the final example, the input is nums equals 0. Here, we only have one binary string of length 1. As before, we start by initializing n equals 1 and an empty result list. Since there is only one index, the diagonal traversal involves just one iteration. For I equals 0, we check the first character of the first string, nums, 0, 0, which is 0. Flipping this bit gives 1, and we append it to result. At this stage, result equals 1. Finally, we join the elements of result to form the binary string 1. This string does not exist in the input array nums, so it is the unique binary string we were looking for in this case. The time complexity of this solution is determined by the operations performed throughout the algorithm. First, calculating the size of the input array nums using len nums is an O(1) operation, as it simply retrieves the length. Next, the for loop iterates through the diagonal of the binary string matrix, running exactly n times, where n is the number of strings in nums. Within each iteration, accessing that ith string and its ith character, as well as appending to the result list, are both constant time operations, O(1). Finally, after constructing the result list, we use .join result to concatenate all characters into a single string, which involves processing n characters and thus takes O(n) time. When we add up the contributions, the loop accounts for O(n), and the join operation adds another O(n), resulting in a total time complexity of O(n). The space complexity of the algorithm is primarily determined by the intermediate data structures used. The input array nums is not modified or duplicated, so it does not contribute to additional space usage. The result list, however, stores n characters as we construct the unique binary string, requiring O(n) space. After constructing the result list, the final string returned by .join result also occupies O(n) space, as it stores the same n characters in a single string. Since these two components dominate the memory usage and both require O(n) space, the overall space complexity of the solution is O(n). When comparing this optimized solution to a brute force approach, the difference in efficiency becomes clear. A naive method would generate all possible binary strings of length n, which would result in 2 to the power of n strings. Generating these strings requires (n*2 to the power of n time, as each string has length n, and checking each generated string for uniqueness within the nums array would add another (n*2 to the power of n). This makes the total time complexity (n*2 to the power of n), and the space complexity would also be (n*2 to the power of n), to store all possible binary strings. In contrast, the optimized solution avoids generating these strings entirely. Instead, it constructs a unique binary string in (n) time and space by leveraging the diagonal elements of the binary matrix. The mathematical guarantee of uniqueness ensures that the constructed string is not in nums, as it differs in at least one diagonal bit for every string in the input. This eliminates the need for exhaustive generation or comparison, making the solution exponentially faster and more memory efficient. The algorithm's time and space complexities remain consistent across all scenarios, whether it's the best, average, or worst case. In all cases, the algorithm processes the diagonal of the binary matrix in a single pass, performing (n) operations to construct the result in (n) space to store intermediate and final outputs. There are no additional computations or branching based on the structure or size of the input beyond this straightforward linear traversal. Therefore, the time complexity is always (n), and the space complexity is also (n), regardless of the input. This consistency ensures that the algorithm is both predictable and efficient in all cases. Here, we highlight some common mistakes to watch out for when solving this problem. First, not accounting for input constraints can lead to unexpected errors. For example, if the array nums contains duplicate binary strings or strings of varying lengths, your solution might fail because the constraints are not properly validated. Always ensure the input matches the expected format. Next, an inefficient brute force implementation can significantly slow down your solution. Generating all possible binary strings of length n results in 2 to the power of n combinations, which can quickly become computationally expensive. Optimized approaches can help avoid this overhead. Another mistake is incorrect binary string conversion. This can happen if you misinterpret binary strings as integers or fail to pad zeros to maintain uniform length. For instance, a binary string like 1 should be padded to 0001 for a length of 4. Using tools like bin and sfill ensures proper formatting. Lastly, overlooking edge cases can lead to incomplete solutions. For example, if nums contains all possible binary strings of length n, your solution should account for this by returning a string of length n plus 1 to handle the situation gracefully. Hardcoding instead of generalizing is another common pitfall. Writing code that only works for specific cases, such as when n equals 3, can cause your solution to fail when tested with larger or unforeseen inputs. Always aim to generalize your logic for arbitrary n. On the topic of interview insights, this problem often relies on the pigeonhole principle. The principle highlights that if there are 2 to the power of n binary strings of length n and nums contains fewer, then at least one binary string is missing. Optimization is key here. Focus on constructing the missing binary string directly using bit manipulation or hash-based lookups, rather than generating all possible strings. During interviews, make sure to test for edge cases. Examples include an empty nums array, maximum possible strings, or strings of length 1. It's also important to communicate trade-offs. Explain why a brute force approach is suboptimal and how the optimized solution improves both time and space efficiency. Now, let's look at some related problems that can help deepen your understanding. For example, LeetCode 287, Find the Duplicate Number, involves a similar concept of identifying a missing or duplicate element under specific constraints. Another relevant problem is LeetCode 136, Single Number, which uses XOR to find a unique element in an array. This is another example of efficient bit manipulation. LeetCode 190, Reverse Bits, is also worth exploring. It involves binary manipulation, which can build your intuition for working with bits in general. Lastly, LeetCode 268, Missing Number, is highly related, as it focuses on identifying a missing element using mathematical properties. Practicing these problems will strengthen your problem-solving skills for scenarios involving binary strings and missing elements. Finally, let's discuss alternative approaches and their trade-offs. One optimized method is to use hashing. Here, you store all strings in nums in a hash set and iterate through potential binary strings of length n. The first string not found in the hash set is your answer. While this approach has a time complexity of 2 to the power of n, for generating binary strings, hash set lookups are 1 per string. The trade-off is increased memory usage as input sizes grow. Another approach is recursive construction. You can recursively generate binary strings while checking them against nums, stopping as soon as a missing string is found. This is easier to implement but may not be the most efficient, with a worst-case complexity of 2 to the power of n. A third option, if applicable, is the XOR trick. If nums can be safely converted to integers, you can use XOR to find the missing number. This has a time complexity of n, but it only works if there's no ambiguity in converting binary strings to integers. Each approach has its strengths and limitations, so choose based on the specific constraints of the problem. Great job following along. In summary, we tackled the find unique binary string problem, explored brute force and efficient approaches, and highlighted key takeaways. Remember to practice similar problems to strengthen your skills. Thanks for watching, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!